We have two people to introduce our speaker tonight, and I would like first to introduce Lou Mayo, who is the father of our speaker.
Oh my
and
goodness.
He was talking to us about a book that Lou wrote in second grade, so I would like to ask him to say a word or two. He came all the way up from Richmond to figure out what his son is doing.
For those of you that don't know me, you know that the science field is totally foreign to me. I'm a criminologist. So, I don't know how he got interested in astronomy, but in the second grade he found a little book he liked. And he stayed with it ever since to this day.
Thank you so much.
Thanks, Dad. This is quite a treat. I've spent a fair amount of my professional life doing things just like this, talking about science, getting kids interested in science, getting the public interested in science. So thanks to Ruth, thanks to Charles Gale, and I applaud the city of Rockville for these programs. I think it's fantastic.
No, it's one on your collar.
It's one on my collar, okay. I have to say this reminds me a little bit of a National Science Teachers Association conference I went to a few years ago. I brought my solar telescope and I set it up outside and hung a sign on it, said we'll show sunspots for food. And I got, I got fed, so. Oh, wait. I know that you're supposed to start with a joke, to loosen people up a little. So I got this great joke. And I made it up. This is my joke. I mean, it's so great. This is so funny. So these two Venusians are talking, on Venus, and it's really hot. It's really hot. And they're complaining about the heat. So they turn on the weather report and they say, the weather says, well, it's going to be another swelter today, about 900 degrees Fahrenheit, and no relief in sight for the next few million years. One Venusian turns to the other and says, I can't take this heat anymore. I just can't take it. And the other says, yeah, but it's dry heat. It's not much water vapor, very small, pretty dry planet. So that's the joke there. So. All right. So tonight we're going to talk about the potential for life in the universe outside the Earth. And I thought I'd just do a quick poll before we get started by a raise of hands. How many people believe that there is life of any type, bacterial or otherwise, outside the universe? Just raise your hand. Okay. Hands down. How many believe there is intelligent life outside the Earth?
Define intelligent.
I'm not going to define it. Just whatever you think. So not as many hands. It's interesting.
Question.
And I haven't even gotten started, and there's a question. All right, go ahead.
Going back to that, are you asking at any point in universe history or intelligent concurrent with our own intelligence?
Gosh, I have no idea. I just came up with this as I was driving here, so you're ahead of me. By a show of hands, how many people believe they have seen something, a UFO of sorts? A couple hands. Put hands down. How many people believe they've been abducted? Okay. How many people want to be abducted? More than that. You'd be surprised. There are a lot of people who believe this. So we're going to talk about potential for life outside the Earth. And this is probably, let's see if I can get this going, what most people think of. Right? right? Isn't this what you think of? Life outside the Earth? These are our fantasies and fears that take shape and become things like this in science fiction movies. But there are other things we need to worry about. I mean, we don't know, right? Or this. Maybe I should read these. The aliens soon regretted their decision to abduct Martha Stewart. And then I found this also. It says, what do you do with it? Looking at a car, and one alien says, I think you're supposed to get into the back of it and make a moaning noise. Are there going to be cultural issues that we can't work out when we find this? So it's an important issue, as you can already tell, right? Okay. So if we're going to take this seriously, and I'm not suggesting we do, we need to start with something. So let's think about how we might go looking for life outside the Earth. Okay. Obviously, we can go there. We send spacecraft to other planets. We've sent people. Where have we sent people? The Moon and low Earth orbit, right? That's it so far. Till we get more funding. Funding, okay? I'll call your congressman. This is the Viking lander. 2 Vikings landed on the surface of Mars in the 1970s. Produced some interesting and controversial results in terms of detecting life on the planet. The Voyager spacecraft that we sent to the outer planets, 2 Voyager spacecraft are now breaking the barrier that is what we call the heliopause, separating the solar system from interstellar space. Mars Reconnaissance Orbiter up there. This is a concept. This is a not funded yet, but a concept to send a spacecraft to land on Europa, the moon of Jupiter. And the spacecraft will heat its way down through the ice sheath that's covering this moon and swim in what we believe pretty firmly to be a saline ocean underneath the ice sheath of Europa. Could there be macrobiotic life, perhaps? That would be the idea. And then, of course, we can send people. It's really expensive to send people. I mean, there are all kinds of additional requirements. You got to bring them back alive. You got to keep them happy. You know, all kinds of things. So, by far, by a factor of 10 and more, the best bang for your buck is to send a robotic spacecraft. But we're explorers, so we do that too. Just better to do it remotely. Another thing we can do is we can look there. So we have telescopes on Earth. These are the twin Keck reflectors on Mauna Kea. The Hubble Space Telescope. Another picture of the Keck. This is the terrestrial planet finder in the upper right. Not launched yet. This is CERTIF, the Space Infrared Telescope facility. Radio telescopes all over the place. Sometimes we need to get above the atmosphere because our atmosphere filters out high energy radiation, most of the ultraviolet X-rays and gamma rays, as well as other frequencies. Water vapor filters out infrared light. So if we want to study the universe in its entirety, we have to get above the atmosphere. And so we build these telescopes, some on the ground and some we launch. We can listen. There's a program called SETI, right? You know SETI, Search for Extraterrestrial Intelligence. And they're listening on millions of frequencies for evidence, for sounds, for signals of intelligent life outside the Earth. Now, it takes a lot of processing power to do this. So you can help. You can go on Google or whatever you use and type in SETI at home, download software. Your computer screen will look like this. And when you're not using your computer, it'll grab some of your computer cycles and use it to analyze some of the data that they're getting back as they're listening for signs of intelligent life. Okay, so maybe your computer would be the one to finally find those signals. You can also pick it up. Stuff is raining down upon the Earth every day. Tons and tons of material. The solar system is a tumultuous place. Things are colliding, falling into each other all the time. Thankfully, a little less often than used to be. One day, something big will hit us, and we're all going to die, and that's just the way it's going to be. But for now, things hit the ground. They become, we call them meteorites. And if we look in homogeneous regions like deserts or the Antarctic region, they're pretty easy to find. Okay? Once we find them, we can analyze the gas content in them, try to figure out where they came from. So it's another, you can just reach down and pick it up. Okay. So if I were to ask you, we know how we can get started exploring, but what kind of conditions are we looking for? What would you say to support life? Name something. Water, excellent. Water. Everywhere on Earth we find water, liquid water, we find life. Everywhere. So that's a good thing to look for. What else? Energy. You need heat, right? If you have no heat, the molecules just kind of hang around and never get together. You can't create complex organisms. Heat is important. What else? Nutrition, some kind of biotic chemistry might be important.
Carbon, maybe.
Atmosphere, maybe. Atmosphere, we like atmospheres here, over here, yeah. And
Carbon, maybe.
carbon, maybe. I see you don't watch Star Trek, ma'am. Okay. Maybe. In other words, what we're looking for is what we know of our Earth and ourselves. And as we look out into the universe, a strange thing happens. We find things we never thought we'd find that cause us to look back at our Earth and find a much greater array of living organisms living in very harsh environments that we never thought would support life before. We used to say that life will live in the Goldilocks zone. Goldilocks zone is the distance from your parent star where liquid water can exist on the surface, and that's the only place you look. We know that's not true anymore. Life wants to survive. Bacteria on nuclear power station rods will repair their DNA. Deep dwellers in the Earth live in places that we couldn't imagine. Giant tube worms live near hot volcanic vents. The diversity of life, as we look more and more inward, is getting extraordinary. It's amazing. So the conditions for life, as a result, are also expanding dust and a compression wave that pulls it together to create stars and stellar systems. And by the way, almost as I'm giving this talk, the information is changing. So I'll have to tell you why I lied in the first part of my talk. But it's now believed that there are at least as many planets in the universe as there are stars. And some researchers are saying perhaps a factor of 10 more. There are, we don't know exactly. We know about the mass of the galaxy, but we don't know how many stars. Something like 100 billion is a reasonable estimate. Let's use it, okay? 100 billion is 10 to the 11th. And we believe there are about 100 billion galaxies. That's 10 to the 11th. That's 10 to the 22nd stars. It's a big number. 10 times that many planets. Who believes there's life potentially in the universe? I love quoting Jodie Foster on this in the movie Contact. Jodie Foster. She asked her dad, she said, "Dad, is there life out there?" And he said, "Well, if there isn't, it's an awful lot of wasted space." Right? You see the movie, that's what he said. Our moon appears to be responsible for stabilizing the tilt of our planet. You learn as a school kid that our planet's tilted with respect to the ecliptic, the plane of the orbit, about 23.5 degrees. By the way, that tilt changes. Okay, these are called Milankovitch cycles. It changes. Not only does that change, but the eccentricity of the Earth's orbit changes, and these are responsible for wild temperature fluctuations in our Earth's environment. But these take place over hundreds of thousands of years, not 150 years like we're seeing now. Our moon may be responsible for stabilizing our Earth's tilt. And It also may be that if life began in tide pools, little protected areas of water, that the tides caused by the moon were partially responsible for providing that environment. Okay, so maybe it's nice to have an Earth-sized moon. Earth's moon is the largest moon with respect to its planet, except for Pluto, which isn't a planet anymore. Right? Plate tectonics plays a role in our atmosphere. Plate tectonics through subduction zones actually carries a lot of atmospheric CO2 with it. Okay? Plate tectonics is also an indicator that you have a hot core. And so probably a liquid outer core and probably a dynamo, a magnetic field. Right? When the core freezes out, no more dynamo, no more plate tectonics. Okay? Except perhaps Europa, which is a different kind of plates. We'll talk about that. Wow, it's really important to have the right kind of star. In the 1800s, Lord Kelvin made a case that the sun and therefore the Earth could not be over so many thousand, and then he modified that so many million years old, because he didn't have the physics necessary to understand how the sun burns. That physics is matter-energy equivalence, E equals mc squared, and quantum physics that allows protons to actually come together and bind together. But the point is that you've got to have a star that lives long enough so that the planets around it can form and take the time for life to evolve. And in the 1800s, the physicists, led by Kelvin, and the biologists and the geologists who were finding different information had this mud fight. I mean, it was heavy, and it was rude. And it turns out that the biologists and geologists are right, that it takes longer for life to evolve than a few million years, at least in our Earth. Okay? So a massive star burns its fuel quickly, lives and dies in a few million years perhaps. Stars that aren't so massive live billions of years, and that's what you want. Our star, the sun, lifetime about 11 billion years, plenty of time for life to take hold and evolve. Well, this is how astronomers think of stars. I just thought I'd throw this up. This is called the HR diagram, or the Hertzsprung-Russell diagram, and it relates a star's luminosity or brightness to its surface temperature or color. And here's our sun right here, with a luminosity of 1, because we get to say that, and a surface temperature of about 6,000 degrees Kelvin. Okay? Stars down here in the main sequence are small enough that they'll live for billions of years. Many of the stars south of, on the graph of the sun, have been around since quite close to the formation of the universe, we believe. Stars up here are very massive. They live, they die, that's it. But as they die, they often take the elements that they created in their core, the elements that make you and me in this table and everything that we know around us except the hydrogen. Helium doesn't bond with anything. And sends them out through the process of supernovas into the universe, and we believe that's how our solar system got formed. This is so much fun, isn't it? Isn't this the best evening you've had in a long time? Well, the right planetary mass. Now this is really important. If your planet doesn't weigh enough, if it's not massive enough, it can't hold on to an atmosphere. So someone back here said they thought an atmosphere is important, and it might be for life. Also, if your planet isn't massive enough, it may not have enough pressure to keep the dynamo going for the magnetic field. Now, it turns out in Earth's core, the heat from the Earth's core is largely due to radioactive decay. But there's also the heat of accretion left over from the formation of the solar system, and the pressure of the Earth as it pushes inward. So these things are important. You don't want to have a planet that's too light. Mars was too light. Poor little Mars. Lost its magnetic field. It's a sad story. I'm going to tell you about it. It may be our Earth's future. Okay, so here we go. Earth. Here's the only planet right now that we're sure has life. It's not a joke. I mean, people have made claims, right? All kinds of claims. But when you get down to it, when you use the scientific method, when you test and retest again, the only place we can clearly say there's life is the Earth. It has a lot of these characteristics that we said were important. Water, heat, atmosphere, life. Magnetic field, circular orbit. We've got the right size star. We're in the right place in our galaxy, not only in terms of the spiral arm, but we're moving actually through a cool place in the galaxy. Not too much high energy radiation. Real nice. Earth is a great place. The oceans, the water, attenuate the temperature of the atmosphere, absorb a lot of the CO2. Sadly, that produces ocean acidification. So that maybe in 20, 30, 40, 50 years, we won't have too many fish around that rely on krill and other animals that have shells for their food source. But anyhow, for right now, mid-latitudes, Rockville, life's pretty good, right? So our atmosphere protects us in a number of ways. And one of the huge things that it does is that it filters out a lot of harmful radiation that we otherwise would get. And this radiation comes in the form of high energy radiation from the sun, ultraviolet, right? We get a little ultraviolet light at the surface and gives us sunburns, right? Not a good thing. But most ultraviolet light is filtered out through ozone absorption. Most X-rays, most gamma rays. This is a really good thing, okay? Cosmic rays as well. Galactic cosmic rays, very high energy particles. They're also stopped to some extent. This is why pilots, airline pilots, have a higher rate of skin cancer than the general public, okay? Because they're flying above, always flying above a large portion of the atmosphere, right? So stay down here. Take the train. So we talked about galactic cosmic rays, which can damage your DNA. Not usually a good thing. This is just a graphic showing, if you measure radiation in units called REMS, you can get a kind of relative sense for how much more radiation you get in space. This is the biggest problem that we have when we start talking about long duration space flights for human beings and colonizing, NASA says don't use that word, but building bases on the moon and on Mars, and now Obama wants to go to an asteroid. I have no idea how we're going to get to an asteroid with people, but he wants to, so we'll do it. But you can see that radiation is a problem, and if you have a solar storm while you're en route, we don't know how to protect the astronauts at this point. Between Apollo 16 and 17, we were sending missions to the moon like crazy, and in the 70s, right? And it just turned out that at that particular time we weren't sending anything, nothing was sitting on the moon, nothing was coming back. And there was a huge coronal mass ejection, a huge solar storm, sending massive amounts of high energy particles and high energy radiation into the solar system. If the astronauts had been en route or on the moon at that time, more than likely they would have been killed. Certainly their health would have been in severe jeopardy. So, space radiation environment, we have to figure this out before we go too much further than low Earth orbit. I mentioned that we're discovering these amazing forms of life on the Earth that live in conditions that 20 years ago, 30 years ago, 50 years ago, we would have thought impossible. Okay? This is a picture of giant tube worms. We find these living and thriving right around hot, boiling ocean vents. You know, try it at home. How long will you survive in boiling water? You know, not long, but these guys do. And they feast off of the elements that come out of the Earth in these hot ocean vents. It's amazing. We also have extremophiles, thermophiles, deep dwellers, lots of different kinds. When we go drilling, you know, drill baby drill. I can tell your political affiliation by who laughs at that and who doesn't. We bring up bacteria from miles under the Earth. Nothing is supposed to live down there, but it does. Yeah?
Any news from Antarctica?
News from Antarctica.
The Russians.
I don't know. What do you want to know? It's cold, it's high, it's dry, it's...
I thought the Russians digging down to that lake.
Yeah.
Searching for
Water.
For water.
Anything there.
Well, I don't know what those results are, but so far, all of our attempts to find life in frozen ice, in water, whatever it is, have been positive. Yeah, water, I mean, life is ubiquitous on the Earth, and all it doesn't need much apparently to survive, and it can adjust, can adapt. So as we start thinking, could there be life on Mars? Mars is cold as heck. And where's the water in Mars? Well, we don't know. It's in ice clouds and permafrost, and maybe under the surface now we're finding more evidence. But could life exist on the surface? Well, there's high energy radiation from a thin atmosphere. It's pretty cold, pretty dry. Well, maybe it could. Maybe it could. Or maybe just under the surface. Okay, with a little protection from the high energy radiation. And I just put this up because I thought it was cool. These are creatures found in some of the deepest parts of the ocean. I don't know what they're called. I don't know anything about them. I found them in the National Geographic. But I just thought, wow, you know, how diverse is life on our Earth? I mean, some of these things don't even look like life. The Dumbo squid. Well, if it has a name, that's good, I guess. Okay, now, given what we've talked about so far, where would you think, in our solar system, where would you want to look for life? You're responsible for millions of dollars, maybe billions of dollars of taxpayer money. Where do you want to look for life?
You got to define what you mean by life.
He wants me to define what I mean by life. Well, I tell you what, I'll do it this way. The Viking landers in the 1970s landed on Mars, 2 landers. They had a number of experiments designed to search for life. These experiments, 2 of which labeled release experiment and the gas chromatograph experiment, basically looked to see if something was exchanging, if there was gas exchange going on in a canister. Okay? So something that is able to interact with its environment, I guess. That's as best I can do. Where would you look?
Moons.
Moons. Which moons?
Well, the ones that are in the habitable zone for their planets.
In the habitable zone for their planets, okay? What else?
If they have water.
Titan.
So, Titan, God bless you, sir. Titan. I spent 20 years of my life studying Titan. I'll give you the $10 later. If they have water, look for places that have water. What do we think? Where do we think there's water?
Under ice.
Why not look for another solar system like us?
Okay, well, we are looking for other solar systems, but in our solar system, where would you look? I mean, I'm going to tell you if you don't tell me. Europa, right? Lots of water, saline water, right? Because the magnetometer twitches as we go by. Well, here are the high target opportunities that NASA has in mind. Mars, Europa, and Titan. Now there are other places we can look. The moon has water, right, in dark polar craters. There are water ice geysers on Enceladus, the moon of Saturn. As we look, we find more places where the conditions for life might be right. But these are pretty high target opportunities right here. So let's take a look at them. So here's Mars. Mars has a kind of a schizophrenic history. Okay, so you remember back when Orson Welles did War of the Worlds, and Percival Lowell looked at Mars in his refractor and he thought he saw canals, or canale, and he didn't. We think maybe he saw the veins in the back of his eye, actually, truthfully. But he thought that clear evidence of intelligent life. Then in the 60s, we sent flybys, Mariner flybys, to fly by Mars, and it looked at Mars and said, oh my God, it's a desolate planet. It looks more like the moon than anything else. It's dry, it's cold, no life could possibly exist there. Then in the 1970s, we sent the Viking missions that I've already talked about, which got somewhat conflicting results from their experiments that dug up dirt, put it in a canister, closed the canister, watched, to see if there was gas exchange, and then at least one of these, and they heated that canister up real hot to try to kill what was in it. And then if they did the experiment again, they'd expect if it was life that they wouldn't see results anymore, and they didn't. But the official word from NASA, and I think it's good to be careful about this, is that all experiments were negative on the Viking landers. But I don't think the story is quite as clear as that. It is possible that we've already discovered life on Mars. Mars, we mentioned a magnetic field might be important. These are magnetometer readings from the Mars Global Surveyor spacecraft showing the frozen out magnetic field in the surface of Mars. It used to have a dynamo. It cooled, the dynamo froze out, no more dynamo, no more magnetic field, but the remnants of that field are still in the surface. So that's how we know Mars used to have a magnetic field. Mars also used to have a lot of water, lots of water. The evidence is very clear from so many different analyses, finding elements, rocks on Mars that only form in the presence of water on Earth, finding flow channels and things of this nature. I'll show you a little bit here. Shorelines, sedimentary features on Mars. This is the famous Mars meteorite. When you magnify it and look up, you see this structure here. Perhaps it's bacteria, perhaps not, we don't know. This is the face on Mars. This is as Vikings saw it in the 70s, as Mars Global Surveyor saw it in the 90s, with a better camera. Sorry, I know no matter where I am, I'm standing in front of someone. I apologize. This is a blurry image with 1970s technology, and a much better image that says, well, it doesn't look so much like a face. It looks like a plateau. So one of two things: either our technology advanced so we know exactly what it is, or the Martians had 20 years to wipe it clean before we sent the next spacecraft. I don't know, I'm not sure which one. Just some evidence of water flows, or evidence perhaps of water flows even on the surface of Mars. Liquid water might be able to exist for very short periods of time. This kind of thing here, this kind of erosion here, very likely indicative of water. We also have ground-penetrating radar now from orbiting spacecraft around Mars that seem to detect the presence of hydrogen below the surface, which is indicative of water. Mars has a real, we believe, a very, very warm, high-pressure, aqueous history, perhaps much like the Earth. Here's some data from various spacecraft and instruments showing up here fresh craters, recent craters that have exposed ice on the crater surface, chloride detections, which are possibly the result of saline water that evaporated, dark flows, in other words, imaging that shows what appear to be the presence of what you might call flow channels, and then the high concentrations of water in the north and south from gamma ray detections of hydrogen. Everything pointing towards a very watery planet long time ago. Here's another image, gypsum, which forms in the presence of water on Earth. This is an Mars MER, Mars Exploration Rover image. Lots and lots of different data sets all pointing to water on Mars, or historic water on Mars. Now there is water on Mars now. There's permafrost water on the surface. There's water frozen out at the poles. There are water ice clouds. But we're looking for liquid water. Okay, my favorite topic is Titan. Well, this is potentially our second Earth. Right? Titan is the largest moon of Saturn, second largest moon in the solar system. It has a nitrogen atmosphere. What else has a nitrogen atmosphere? Earth. It has lakes. It has rivers. It has clouds. It has weather. It has rain, it has seasons, and I'm selling lakefront property out here later, so come on by. Turns out that when our sun becomes a red giant, one possibility is that the atmosphere clears up, the water comes out of its frozen state, surface temperature is now 92, 95 Kelvin or so, and so the surface warms up, and it could be a place that we could live if people are still around at that time. This is a very old image of reflectance on the surface of Titan. This is the best we had until we sent the Huygens probe and the Cassini spacecraft. I'll show you this in a minute. Oh, let me just make one other statement. This is Titan. We're not seeing the surface here. It's got smog in it. It has this, these very long chain polymers that are the result of photochemistry, ultraviolet light interacting with nitrogen and methane in the atmosphere, creating this kind of smoggy gunk, but also responsible for this amazing array of hydrocarbons and nitriles in the atmosphere. Truly, truly prebiotic atmosphere, producing things such as hydrogen cyanide, which is a building block of amino acids. This is a Cassini image. Cassini was designed to see through the clouds in places where methane doesn't absorb so strongly. We can see to the surface, we can see hydrocarbons, we can see water ice, we can see organics, we can see methane clouds. I mean, there's not much not to like here, except that it's really, really cold. When we pass a spacecraft by Titan, we can measure its density if we know its volume and the distance from it. And its density is less than 2 grams per cubic centimeter. This means there's a lot of water ice in the planet, in the moon itself. Perhaps liquid water far below the surface. Here's a picture of the Cassini spacecraft with a Huygens probe that is going to drop into the atmosphere of Titan. There's Saturn. These are paintings, of course, of what it might have looked like as the probe descends through the atmosphere. 50% greater surface pressure, by the way, than we have here on Earth. What it might have looked like when it landed, it had a little spring-loaded thing on the bottom that wanted to find out what the surface was like. So if it landed on something hard like this, the spring would collapse a lot. But if it landed in water or some liquid, the spring wouldn't collapse at all. It collapsed a little bit. So kind of like wet sand or something like that. It has a camera. The Huygens probe had a camera that, downward pointing camera. And it took this mosaic of the surface of Titan. I mean, these are amazing images. These dark areas here are liquid on the surface. The brighter areas here are hard surface. You can see flow channels here already. Some of these white patches here are methane clouds. Methane takes on the role of water that water does on Earth. It's so cold on Titan, water's frozen out, but methane rains, evaporates, forms clouds, rains, so there's a methane cycle. When it got to the surface, it took some pictures of the surface. These are probably water ice coated with tholins, very complex hydrocarbons. Liquid here of some sort, probably methane-ethane concentration. That's what we believe is raining down on the surface with some other hydrocarbons mixed in, and nitriles. And then over here you can see this really intricate set of rivers. Coming a little closer to us around Jupiter is the moon Europa. Europa, one of the 4 Galilean moons, right? You can see them in small telescopes, Io, Europa, Ganymede, Callisto. Europa is believed to have a saline ocean underneath an ice sheath. And the reason we believe there's a saline ocean there is that when we send a magnetometer flying by, the magnetometer twitches. And knowing other things such as the density of the moon and some surface features that we believe are floating on something, we believe that there's something carrying electricity through the, kind of interacting with the Jovian magnetic field. And this is probably a saline ocean. It has lots of cracks in the surface. And it has a lot of features that look like they should fit together, but they're far apart. So these icebergs, if you will, are kind of just floating along the surface of Europa. This is a Galileo image, Galileo spacecraft image. We also see some evidence of what might be some kind of sputtering or geyser activity on Europa. So perhaps some interaction between above the ice and below the ice. Okay? And so this might be an important question to answer. Can you get material, can you get nutrients down below the surface? And perhaps through impacts, you can do that. Well, there's one other type of solar system object I want to talk about, and that's comets. Best evidence we have to date is that our Earth formed dry. Water could not condense in the inner solar system. Hydrogen was blown out by our solar wind to create the Jovian planets. So then where did our water come from? And one possibility are comets or asteroids. So we'd like to look at the water we have on Earth and see if it's the same kind of water that's in these comets and asteroids. And one of the ways we're doing this is we're looking at what's called the D to H ratio, the deuterium to hydrogen ratio. Okay, there are two kinds of hydrogen, well there are others, but deuterium, which has about twice the mass as just your normal hydrogen, but both can form water. So deuterated water has a certain small percentage in every glass of water you drink. Oh my God. But in our oceans and also in comets. So we're looking for those ratios. If we can find similar ratios, then maybe we know where the water on Earth came from. We also see evidence of amino acids on comets. So perhaps comets brought the building blocks of life to Earth and seeded them here. Perhaps they came from Mars and some major impact collision blasting stuff off the surface of Mars. We know for a fact that some of the meteorites that we have in our possession came from Mars because we can measure the isotopic ratios of the gases in the little gas bubbles inside these meteorites, and they match the isotopic ratios in the atmosphere of Mars today. So where did it all come from? Well, we're trying to answer those questions. So let's go outside our solar system now. I have no idea how much time I have. I'm just going to talk till I'm dragged away with this out of my cold dead fingers.
There'll be a music program starting at 8:30.
That'll drag me out of here real fast. Okay. There are a number of ways that we look for planets around other stars. So we're leaving our solar system now and going to look for planets around other stars, and maybe planets with favorable conditions for life around other stars. So 6 ways of looking for these planets. You can look for their cross-track movement of the star as the planet pulls on it as it goes around. You can look for the Doppler shift in the spectral lines of the star as the planet pulls it closer and further away as it goes around. You can look for the light dipping if the planet moves in front of the star as we see it. The star's light will dip for a while and then dip again. Okay, it's called a transit detection method. You can look for spectroscopy. We can actually detect some very few atmospheres of these planets. We see gases that should not exist in the star. It's too hot, so we assign them to the planet. Gravitational microlensing. As a star moves in front of a star because of general relativity, it actually warps space in a way that lenses or magnifies the starlight behind it. And planets can do the same thing. And then, of course, maybe the Holy Grail is to actually see it. And we've actually imaged a very small number of planets around other stars. This is Beta Pictoris. This was the first planet found to orbit a sun-like star. I think it's the second extrasolar planet detection. The first was around a neutron star. This is it's a fairly young system. Still got a lot of gas and dust that's coming together. A lot of accretion processes going on, creating perhaps more planets. But here is Beta Pictoris b. That's the planet that was discovered, and that kind of got the whole thing going. That was the first planet around another star. Here's a planet transit detection method. This is actual data from a star called HD 209458. You all know that one, right? So we kind of give the star would be A, and then if there's a planet around it, it would be B. If there's another planet, C, D, E, and so on. And here we have actual data showing the photometric data of the starlight dipping and recovering and doing that periodically. And when you see this, you can tell all kinds of things about the planet and the star. If you look at the period of time between the dips, if you look at the angle of the dips, you can get a pretty good idea of how big the planet is, what the orbit's like, and if you know something about the spectroscopy of the star, how big the star is and what kind of the star is like. This is the radial detection method. As a planet orbits a star, it pulls on it, right? It's got a little bit of mass. And as it pulls on it, the star comes closer to us and further from us. And so we can see the change in the frequency of spectral lines of that star called the Doppler effect, which is what you hear every time there's a police siren that goes by you. It goes, meow. Happens with sound, happens with light too. So we can detect the presence of something orbiting that star, maybe another planet, other ways to decide, by looking at Doppler shift of the spectral lines. We can sometimes detect gases in that planetary atmosphere. This is a sodium detection in a planetary atmosphere here. And it's just, these happen to be lines that you wouldn't expect to see in the spectrum of the star. So I'll tell you, I'll bet you we know of more planets now than we did when I started talking. The number of confirmed planets is skyrocketing, okay? And this is partly responsible for these statements that there are as many planets, or perhaps even more planets than stars in the universe. 2,326 candidates. A lot of these are from the Kepler mission. Kepler is a spacecraft that is looking at about 200,000 stars at the same time, looking for evidence of these photometric dips, transit detections. 760 of these possibilities have been confirmed as planets to date. Okay, so you see the dip, you don't know what it is it a brown dwarf star orbiting or whatever, and use other methods to confirm. 760 planets we now know, confirmed. Over 400 potential multi-planet systems. Isn't that amazing?
Are they all in our galaxy?
All in our galaxy, that's right. All in our galaxy so far. And we're only looking at a tiny, tiny part of space. You know, a few thousand. It's not hard to believe that if you just say, this is how much space we're looking at. We found maybe a few thousand here. How many in the whole of the galaxy as you look around the sky? Millions, maybe more. Billions, I guess is what I started off with, right? This is the Kepler spacecraft. I mean, this is an artwork, but here looking at a transiting extrasolar planet. Okay. This is a paper on Kepler 22b. This is a multi-planet system that Kepler seems to have discovered. And it's important because one of these planets orbits within what we believe would be the habitable zone, right, the Goldilocks zone of that star. It's a sun-like star. It's a main sequence star. And so perhaps this increases the chances for finding life on this planet. This is just a graphic showing the relationship between the distance that a planet is when we find it around its star and the number of planets that we find. We find a lot of them that are really close in. This AU, astronomical unit, is 1 Earth-Sun distance. So here we have half the distance to the Sun out here. A lot of the planets we find are really close in. And that makes sense if you're using the transit detection method, because if you have to have the orbit right in the plane of your sight, if the planet is very far away, then a slight changes in the inclination of the orbit and you won't see the planet passing in front of the star. This is just a consequence, I think, of the geometry and the detection method. Here's another way of looking at it. Orbital period versus the size of the planet, or radius or diameter of the planet. Orbital period in days, this is a log scale, so 1, 2, 3. So there's about 1 year. That's about where our Earth is, 365 days roughly on that scale. Just gives you a sense of the kinds of planets we're discovering. These are Earth-sized planets down here, Neptune-sized planets here, Jupiter's and large Jupiter-sized planets up there. Many of them orbiting, look at this, some of them even less than a day orbiting, really close to their parent star.
Colors and shapes?
Different detection methods, different instruments, and I'm sorry I don't know which ones are which. Another multiplanetary system, Kepler 11.
Detection methods biased against, are favorable towards large planets close to the star.
Sure.
So you're not,
Large.
part of the reason you're not seeing many Earth-size in the nice Goldilocks zone.
Right. The comment, which is correct, is that these detection methods are biased towards large planets. Large planets block out more sunlight, have more of a, if they're more massive, they have a larger gravitational lensing effect. They'll pull more on the star if they're more massive. I'm saying massive and large in separate sentences here. So your radial detection and astrometric detections are more likely. So really the challenge is first find large things, then get better detection methods and look for Earth-sized planets. This was just a cover story on Nature of Kepler-11 multiplanetary system. And that system looks a little bit like this. Here's the orbit of Venus, so it's about something like 7/10 of the distance from the Sun as the Earth is. And the planets in the Kepler-11 system are all orbiting within that, so very short periods relative to our solar system. Kepler-11 planets down here. Here's Earth, just relative sizes. Here's Jupiter, and so on, and some other planets we've discovered. So we're really seeing a wide variety of sizes, masses, compositions now. Rocky planets, perhaps, gas giants, super gas giants, super Earths. And I really like this. This is this is made up. Okay, it's a picture. It's a artwork. But this was a comment made by one of the astronomers at the SETI Institute. He said, planets are like bunnies. You don't just get one, you get a bunch. Seth Shostak at SETI said this. So really the number of planets in the Milky Way is probably like 5 or 10 times the number of stars. That's something like 1 trillion planets just in our galaxy. So I'll leave you with that awe-inspiring thought. That's my last slide, and I'll take questions.
What is the status of SETI, and what do you think is its potential?
What is the status of SETI, and what do I think is its potential? Well, it lost either all or most of its NASA funding. Planetary societies doing good things with it. So far, it hasn't found anything. So it's really polarizing the community of people who think about such things. Some say, well, yeah, there's nothing out there. And some say, well, we're not looking in the right places in the electromagnetic spectrum. So it's kind of hard to say what its potential is. I mean, I trust Jodie Foster. I think, it's just what I think. I mean, I can't, but as we discover more and more and more and more planets, I'll just say it gets more intriguing, more compelling. It's not a great answer to your question, but we'll see, I guess. Yeah.
Do you think if we didn't have our magnetic field, would we as humans have adapted to the problem of radiation?
If we didn't have a
If
we didn't have a magnetic field, would humans, and maybe you mean life in general, have adapted to increased radiation? Well, if we didn't have a magnetic field, over periods of millions, 100 millions, billions of years, we would have lost probably a good part of our atmosphere, and with that, water vapor. Water could have resided below the surface, or if it evaporated, eventually it would be a part of photochemistry. It's separated into hydrogen and oxygen. Hydrogen's light, it goes away easily. Would we have adapted? Well, we know of life forms on Earth that do adapt.
Yeah.
They're simple life forms, but perhaps if given long enough, we could have adapted. Now you said humans, right? So the question is, would there be humans? In fact, here's an interesting problem I'll leave you with too. Of course, we all know about dinosaurs. You know, if you're in 3rd grade, your two things that you get real excited about: dinosaurs and space. Why did the dinosaurs go away? Why?
We don't have any proof of anything.
Here's a good critical thinker. We have no proof of anything. Maybe you're right. But we do find large regions of elements that we only find in asteroids that we don't find much of on the Earth, indicating large-scale impacts. Okay, so the prevailing theory is that the dinosaurs went away because some massive object, and we see evidence of these mass extinctions throughout our Earth's history, whacked the Earth, debris went all over everywhere, blotted out the sky, plants died, dinosaurs died, only little things survived, like our ancestors. If Earth had been 1 minute later in its orbit, or that asteroid or comet had been 1 minute earlier or later in its arrival, it wouldn't have hit. You know, well, there hasn't been, and there will be. We're all going to die. It's true, but at that time, it would, you know, perhaps the dinosaurs would not have died off, and we wouldn't be here. Yeah, you and then you.
Well, I better let my wife go first.
There you go, sir. That's right.
I'm not a scientist, but I do wonder what your thoughts are about all this, you know, these guys, and all the, you know, increase, the exponential increase in all the, you know, the waves and the stuff, the satellite stuff, and the, you know, cell phones and Wi-Fi everywhere. I mean, is that, because that's happening very quickly, and I'm not understanding how that's able to, first of all, happen, and is it increasing, or is it just drawing on stuff that's already been here? If that makes any sense, I don't know.
I'm struggling a little, but I think if I can interpret your question, today we have a lot of radio and microwave radiation going through us right now. Are you worried about this, ma'am?
Well, I'm just saying, I wanted your take on it. Has it always been here, or is it now?
Oh, no. It's very clearly, we're creating this stuff.
And it's happening very quickly, so that's what I'm saying, adaptability-wise. If we're sort of saying, well, everybody's got to have one of these, and we go launching off in that direction.
Are we adapting to this increase in density of radio and microwave energy? Well, here we are. You know, the population just reached 7 billion. There are no studies that I'm aware of that show that the general radio wave environment that we live in is harmful to us. Of course, there are studies about cell phones and putting them right up to your ear like this, and nothing's definitive yet.
Relatively recent.
But I think, you know, maybe it's reasonable to think about this. In fact, we're just about ready to saturate our the radio frequency ranges that we have to transmit with. Cell phones are going to get, if we don't find more bandwidth, cell phones are going to get more inefficient. Yes?
Two quick ones. You mentioned about the molten core of the Earth.
Outer core, yeah.
What keeps it from cooling down at a sufficiently rapid rate?
Radioactive decay. Radioactive decay in the Earth's core is the primary heating mechanism that keeps things hot in the core, keeps the outer core
So it's not
hot.
likely to diminish at any reasonable
Well,
rate?
it will, you know.
Very slowly. And then the other thing is you mentioned about flying in a jet plane above the protection of the atmosphere from radiation.
Right.
If